In this video, we're going to begin talking about our module on reaction stoichiometry, which is using chemical equations to calculate quantities. The learning objectives for this module include applying stoichiometric relationships to calculate amounts of substances involved in chemical reactions, identifying limiting reactants, and also calculating percent yield. We will begin by talking about molar ratios, which are also known as stoichiometric factors. This is part of the learning objective for applying stoichiometric relationships to calculate amounts of substances involved in chemical reactions. Before we begin, let's write a balanced chemical equation for the reaction depicted in these boxes. In this before reaction box, we can identify the chemical species as O2 and SH2. So this one is SH2 and that's O2. After the chemical equation, we look for new substances that were not present before, and we see that we have SO2 and H2O. And now we have to balance the equation. I see a total of 3 oxygens here and a total of 2 oxygens here. So I'm going to go ahead and boost this up so that that's a 6, and then I'll try to get that up to be a 6. So I could put a 2 there. That'd give me 2 sulfurs and 4 oxygen. And so I could put a 2 here and a 2 here. And so that gives me 4 hydrogens, 4 hydrogens. That gives me 2 oxygens plus 4 is 6 oxygens, 2 sulfurs, 2 sulfurs. So I believe we are balanced now in this chemical equation. And so what this chemical equation is telling us is that for every 3 molecules of O2, I'm going to react it with 2 molecules of SH2. So let's go ahead and circle that. So 2 SH2 and 3 O2 molecules. And so this tells us the ratio in which things react. And so this is one reaction worth. I'm going to abbreviate reaction as RXN. And this is a second reaction. So we have enough substances present so that we can do this reaction twice. And so that means that I should be able to get 4 SHO2s out and 4 waters out. And so let's find them. I will have 2 SO2 and 2 H2S. I'll go ahead and circle this bottom one here. It looks a little bit, I think it'll fit in the circle better. Here's one reaction. And then we have a second reaction. And we'll see here that we have leftover SH2 that is present in both before reaction and after reaction because we did not have enough O2 to react with all of the SH2. Our balanced chemical equations do not tell us what we're starting with. They just tell us the ratio of how things react. We will be using this balanced chemical equation in later videos. Alright, so these molar ratios in those stoichiometric coefficients in our balanced chemical equation tell us the proportion in which things react. Much like the quantities in a recipe tell us the ratio to put in into our reaction when we're cooking. So for instance, if we are making chocolate chip cookies, we need 1 teaspoon of salt. We do not need the entire canister of salt. We just need a teaspoon of it. We will most likely start with more salt than what we need, but we'll be able to put the extra salt back in the cabinet and use it as a later date. Same with the butter and the eggs and whatnot. If you need to double this batch, then you have to double every single quantity on here. And if you don't have enough eggs or something to double everything, then you're going to need, you can't actually double everything. So you're going to run out of an ingredient at a certain point. But you have to maintain these quantities, otherwise your recipe is not going to taste good. If you use way too much salt, you're not going to have edible cookies. And if you don't have enough eggs, it's not going to have the right texture. So you have to follow these ratios. And it's the same for our chemical equations. We follow the proportions outlined by the coefficients in our chemical equation. So our stoichiometric coefficients will relate our reactant to a product to another reactant, a product to another product, or a product to a reactant. We're always picking pairs of things to compare. So one reactant to one product, one reactant to one other reactant, always comparing two things at a time. These types of calculations are very useful when you're trying to predict how much do you need to start with, what would the estimated cost of reaction be, and trying to reduce costs by not having large excess amounts. So let's take a look at those stoichiometric relationships. So you see here these coefficients that are highlighted in blue. That's what we're looking at. Before we were talking about individual molecules, like two molecules of H2S would be proportional to 3 molecules of H2S. But we know that there are 6.022 times 10 to the 23rd molecules in 1 mole. So if I used 24 molecules, I would need 36 molecules of H2S. And if I start with 2 moles, I would need, let's just say H2O. H2O, O2. Oh my god, I can't talk. That's O2. These are the H2S ones. If you have 2 moles of H2S, then you'll need 3 moles of O2. So for every 3 moles of O2, you will need 2 moles of H2S. For every 3 moles of O2, you're going to be making 2 moles of SO2. We're just looking at these coefficients that have been circled and they're in blue. For every 2 moles of SO2 formed, 2 moles of H2O will form. So you can see we're just picking any 2 combinations. You compare that one to that one, that one to that one, that one to that one. Like, you just pick pairs at a time and compare them. So we can use those proportions to do some calculations. For instance, it says how many moles of H2S are needed to react with 5.24 moles of O2. So if we start with our 5.24 moles of O2, then we can use our molar ratio, which is also known as our stoichiometric factor. I'll write that down. Then we need to cancel out our moles of O2. And then we need to get into moles of H2S, because that's what we're trying to find. And that will give us moles of H2S. Now for the numbers. The 3 is attached to the O2. the 2 is attached to the H2S. So we can do 5.24 times 2 divided by 3. So 5.24 divided by 3 is 3.49 moles of H2S. For our next one, it says we're asked to find how many moles of SO2 can form from 5.24 moles of O2. So now we're comparing these two. Before we were comparing those two. So now we do 5.24 moles of O2, cancel out our moles of O2, and then get into what we're looking for, which is moles of SO2. That is a 3, that is a 2, and so we're going to end up with the same number that we had above. Only now it's going to be of SO2. So here's a practice problem for you. Go ahead and pause the video and try to work this one out on your own. It reads, how many moles of H2O are formed if 3 moles of SO2 formed? Unpause the video when you're ready to continue. Alright, let's go over this. Did you select that it's impossible to determine? No, we know this. Let's do this. If we have 3 moles of SO2, then we need to cancel out our moles of SO2 and get into moles of H2O. So that is a 2 here, and that is a 2, and so that's going to be equal to 3 moles of H2O. Our moles of SO2 cancel. 2 over 2 is 1. 3 times 1 is 3. So 3 moles of H2O.